Example 2, minimizing cost. A cylindrical can is to be made to hold 1 liter of oil. We want to find the dimensions that will minimize the cost of the metal to manufacture the can. So again, what we're dealing with is a cylindrical can, and we want to find the dimensions that are going to minimize this cost. So first thing is we need to design a picture. So let's take a look at the picture here, okay? So here is our cylindrical can. Okay, we have a circle at the bottom, circle at the top, okay? And what this represents is we have a height and we have a radius, okay? So if we break this up into pieces, okay, we can see that this represents the top of the cylindrical can, and this represents the bottom of the cylindrical can, okay? So we have a circle that has a radius r. So we know that the area for those two circles is going to equal, since there's two of them, it's going to be 2 times pi r squared. So that represents our circle at the bottom and on the top. Now we need to look at the inside of the can. Okay, now keep in mind here that in order to find the area of this, okay, we know that the circumference of that circle is 2 pi r. And we have a height of h. So if we flatten this out, we would have a rectangle. So that means that that rectangle is going to be the length times the width, or in this case, it's going to be the height times the circumference, which is 2 pi r. So therefore, this area is going to equal the circumference, which is 2 pi r times the height of h. Okay, so what does this give us? Well, what this tells us is that we want to be able to find the area of this. Okay, and the area is going to equal, we're going to take 2 pi r squared, and then we're going to add the circumference, which is 2 pi r times the height. So we're going to add those two areas together. And then what we want to do is we want to minimize the area A. Okay, so what is given? Well, what's given is the fact that we have a volume, and that volume is 1 liter. Okay, and if we want to convert that 1 liter into cubic centimeters, well, we can set that equal to 1,000 cubic centimeters using that conversion. Okay, so now the next thing that we want to do is we want to be able to figure out, okay, what is the height according to the volume? Well, we're given the volume, right? And what is the volume of a cylinder? So that's the next information that we need. We know that the volume of a cylinder is equal to pi r squared h. Okay, and so what do we know about the volume given in the problem? We know it's 1 liter. Okay, or it is 1,000 cubic centimeters. So we're going to rewrite the volume to be 1,000 cubic centimeters, and we're going to solve for h, because we're going to want this formula to be in terms of our radius. So if we want to solve for h, we need to divide both sides by pi r squared. So h is going to equal 1,000 over pi r squared. So now what we want to do is now we're going to use this formula and substitute what we got for h into step number 1. So using that formula, we know that we're going to have the area, which is equal to 2 pi r squared plus 2 pi r times 1000 over pi r squared. Okay, so now what we can do is when we multiply this out, okay, we can simplify the pi and the r. So therefore, we're going to get 2 pi r squared plus 2 times 1000 is 2000. We know that we can simplify the pi, and we know that we're going to have an r left in a denominator. So therefore, it's going to be 2000 over r. And so what this tells us is that r has to be greater than 0. Okay, so now what we want to do is we want to be able to find the critical numbers. And so in order to do that, we need to find the derivative, or a prime of r. So if we find the derivative of what we just found there, so the derivative, okay, according to r, well, if we look at the step beforehand, it's going to be 2 times 2 pi, which is going to be 4 pi r. And then that's going to be minus, because this is 200 over r, which is the same thing as 200 to the r minus 1. So it's going to be minus 200, or 2000, excuse me, over r squared. Okay, so let's find the common denominator. So we should know that the common denominator, in order to simplify this into one fraction, is going to be r squared. So if this is over 1, you're going to multiply that by r squared. You're going to multiply this by r squared. So we're going to get 4 pi r cubed minus times 1 here, 2000. Okay, and now if we rewrite this as one fraction, so we're going to combine the numerators. So we have 4 pi r cubed minus 2000 over r squared. Okay, and so now what we want to do is we want to be able to determine the critical number by setting this derivative equal to 0. So we're going to set the derivative, which is 4 pi r cubed minus 2000 over r squared, which is equal to 0. Okay, so if we multiply both sides by r squared, well, then what we're left is 4 pi r cubed minus 2000, which is equal to 0. And if we add 2000 to both sides, we get 4 pi r cubed, which is equal to 2000. If we divide by 4 pi, then r cubed is going to equal 500 divided by pi. And so therefore, if we take the cube root of both sides, then r is going to equal the cube root of 500 over pi. So what does that tell us? Well, that tells us that there's only one critical number, right? So there's only one critical number, and that's in the interval between 0 and infinity. Okay, now next, let's take a look at the visual of this graph of the function, which is the area, which is equal to 2 pi r squared plus 2000 divided by r, where r is greater than 0. Now, when we put this into Desmos, we're not going to write r, we're going to use it as x. So let's go ahead and graph this. So we're going to put in 2 pi x, and that's going to be plus 2000, and then we're dividing that by x, and then we also know that r has to be greater than 0, so we're going to say that x has to be greater than 0. Okay? And that should be squared. Okay, so here's our graph. Let's take a picture of that. Make sure that point is located there. Okay, so this is what our graph would look like whenever we would have the area is equal to 2 pi r squared plus 2,000 over r, where r is greater than 0. Okay, so let's point out the fact that the cube root of 500 over pi is approximately 5.419, which means that this represents our critical number. Okay, so we can say two things here. Okay, so the two things that we can say are the following. All right, we can say that the derivative, okay, is going to be less than 0 for r being less than the cube root of 500 divided by pi. And we can say that the derivative function is going to be greater than 0 because it'll be increasing for when r is greater than the cube root of 500 over pi. Okay, so what that tells us is the following. Is that the area is decreasing here for all r on the left of the critical number and increasing for all r to the right of the critical number. And so what that tells us is that we have an absolute minimum where r is equal to the cube root of 500 divided by pi. So now what we're going to do is we're going to substitute this value of r so that we can determine what h is. So we're going to let h equal 1,000 divided by pi times the value of r, which is the cube root of 500 over pi squared. Okay, so what we're going to have to do is we're going to have to sort of use some algebra here. So we got 1,000, and then that's going to become pi times 500 over pi to the power of 2/3. Okay, and so now what we're going to do is now we're going to distribute that exponent. So we have 1,000 over pi times 500 to the 2/3 power over pi to the 2/3 power. So therefore, we're going to rewrite the pi to 2/3 power into the numerator. So we end up getting pi to the 2/3 in the numerator times 1,000 over pi times 500 to the 2/3 power. Okay, and now what we can do is, if we want to get the same base, right here we have the same base of pi, over here we want the same base. So we can factor out a 2. So if we factor out a 2, then we have 2 times pi to the 2/3 times 500 over pi times 500 to the 2/3 power. Okay, and then from here we can use the same base rule. So what that means is if we take pi to the 2/3 and divide that by pi to the 3/3, well, that gives us pi to the negative 1/3 times 500 to the 1 is the same thing as 3/3 minus 2/3 is going to give us 500 to the 1/3 power. Okay, and so if we want to write that pi to the negative 1/3, well, we can leave this in the numerator, which is 500 to the power of 1/3 over pi to the power of 1/3. Okay, which is the same thing as 2 times 500 over pi to the 1/3 power. And if you recall, that's going to equal the same thing that we have for the radius over here. So that's going to be 2 times the cube root of 500 over pi. Well, we know that that equals r. So therefore, that's going to equal 2 times r. So when we let the absolute value r equal to the cube root of 500 over pi, we found out that h is going to be equal to 2r. Well, what does that mean? Well, that tells us that to minimize the cost of the can, the radius should be approximately 5.419 centimeters, and the height should be equal to 2 or twice the radius, namely the diameter. And recall that that 5.419 centimeters is the cube root of 500 over pi.